Okay, so here's today's molecule. It's called, well, its common name is isooctane. This is a constituent of gasoline, makes up about 10% of most gasoline. And it is the sort of the standard set point for 100 octane fuel. So the octane rating is a measure of resistance to engine knocking, which is like premature detonation of the fuel inside the engine. And so isooctane is very resistant to engine knocking. The opposite would be N-heptane, which is set as 0. And so that means it's more likely to detonate early inside the engine. You probably know that most gas at the gas pump is sort of like upper 80s, 90s octane. And so that means that gasoline that we put in our cars is pretty resistant to engine knocking. Um, Sorry, I'm a car nerd. Um, Diesel fuel, on the contrary, you want that to combust more easily under compression in an engine. And so diesel fuel has a really low octane rating. So that's where the term octane comes from. But if we go and think about doing an IUPAC name for this molecule, what is the parent chain? How many carbons does it have? 5. So why is it called isooctane? Because it's got 8 carbons total. So that's actually a good point of differentiation between common names, which might have the octane part is referring to the total number of carbons in the molecule. But if we're going to do an IUPAC name for this, 1, 2, 3, 4, 5 carbons is the longest chain. So it's a pentane. And our substituents are all methyl groups. So we've got methyl groups on, well, how should we number this? Probably from the left, because that puts 2 of our methyl groups on carbon 2 and 1 of them on carbon 4. So methyl on C2, C2, and C4. We've got 3 of those. So that's going to give us trimethyl. And so our overall name is 2, 2, 4. Trimethyl pentane. Isooctane is easier and more fun to say, so that's its common name. Okay. Questions on that, how we got that name? Cool. So of course, just make sure that your parent chain is the longest continuous chain of carbon atoms and not the total number of carbons. That doesn't follow the IUPAC rules. Okay, the only like new piece of material that we have left is if we have halogens on our molecule that we need to name. So we'll use this example. Is that correct? That should be 1, 2, 9 carbons. So what if we have a molecule like this? Okay. Your instinct is going to be wrong in this case. Your instinct is probably going to be to look at that horizontal chain because that's the longest continuous chain of carbons. And that's what I told you to use for the parent chain. If we do that, we would have something like 1, 2, and do this in pencil because I'm going to erase it in a second. We do something like this. And okay, we have the substituent on carbon 5. but you'll notice that we have a CH2 and an F, and those are attached. The F is attached to the CH2, which is attached to the carbon number 5. And so I haven't taught you how to name that, and we're not going to talk about that because this is not the correct way to number, or this is not the correct parent chain. So the rule here for halogens is that the parent chain should include the halogen if you can. And I think in all cases that I will show you, it is possible to include the halogen in the parent chain. And so that means that our parent chain has to include, okay, actually I should, includes carbon with the halogen, really is what I should say, because our parent chain is going to start there at that carbon. Right, the parent chain still has to be a continuous chain of carbon atoms, so the fluorine can't be atom number 1. But number 1 is going to be the carbon attached to the fluorine, and we'll go away from it. In this case, it doesn't matter if we go to the left or right, because they're the same size. And of course, we number going from southeast to northwest, because if we did it the opposite direction using the same carbon atoms, we would have a substituent on 1, 2, 3, 4 carbons 5 and carbon 6. And that's certainly not what we want. So we need to go this direction. Okay, so now, well, now we just treat it like any other molecule. So our parent chain is 6 carbons long. It's a hexane. Let's see. Okay, so we've got 2 substituents. We have the fluorine atom, and that's on carbon 1. And then we've got what kind of chain on carbon 2? Ethyl would be a chain that is 2 carbons long. But this chain is 1, 2, 3, 4 carbons long. Yeah. So that is butyl. Let's see, 2. Now, for the halogens, we're going to slightly modify the ending of the halogen name in order to make it a prefix. So for naming purposes, and I think these come pretty easily, fluoro, chloro, bromo, iodo. So that makes this, well, we'll start with butyl because that's first in the alphabet. So this is going to be 2 butyl, 1 fluoro hexane. Now, this is a bit of a more complicated example of an alkyl halide, right? That's what this functional group is. This is a more complex example of naming an alkyl halide because the parent chain isn't the longest chain, because the longest chain does not include the carbon with the fluorine on it. But if we had, for example, this molecule, we don't have to worry about the longest chain not being the parent chain. So this would be 3-bromo pentane.
What about the two on the side that you missed?
The two on the side.
So bromine started, there'd be one right there, and be 2, 3, 4. No, the
Yeah, so in this case, the parent chain is there because it's the longest continuous chain of carbon atoms, and it has the halogen directly attached to the parent chain. And so we can give the halogen a number, in this case, 3-bromo pentane. But on the fluorine example, if we had the horizontal chain just be the parent chain from 1 to 9, the fluorine would not be attached directly to the parent chain. It's attached to a carbon, which is then attached to the parent chain. So it's not directly on one of those carbons. And because of that, we need to change the parent chain to make the fluorine go on the parent chain. We'll see a couple examples of this sort of thing in a second. But you know, this difference between whether something is directly attached to the parent chain or not doesn't come up too often. Really, the main thing here is get those prefixes. Okay. What practice do we want to do first? IUPAC naming or functional groups? Functional groups? All right. So you'll need your chart for this. So go ahead and work with the folks next to you and label as many functional groups as you can in these molecules. The one thing I would say is, as you're going through these, is make sure you don't just look at the interesting atoms in the functional group. Make sure you look 1 or 2 atoms to the side to make sure that you don't have a more complex functional group. So an example of that would be in A here, you might see that OH and you go, oh, that's an alcohol. But look past it and you'll see that there's a C double bond O, a carbonyl, right next to it. And that together is a different functional group than an alcohol. All right, so give that a shot. Did you get yours? Oh, that's right. Sorry. It's okay. Actually, I wanted to yeah. Yeah.
Spectrum, fire, stuff.
No, that's significant. Yeah, what's the you expect? Maybe drive. All of this stuff is kind
We are.
of. Yes, and we did gaming. Last stuff.
Oh, no, we are.
Yes. Yeah. No, I did. Oh, yeah, because it was one worksheet including drawings, skeletal structures and that stuff. Those are the ones you take, and I included those things in there, and then I had a shaping stuff.
Yeah, there's
Like G and H. Which one? It's the last two ones.
I don't recognize it's like.
Oh, no, they're just random. You have to make them up. All the other ones I think are real. Thumbs. But I was like, this is a bunch of groups. I need some sort of make it put it on the first molecules. Yeah, I'm going to much of that one, but that makes sense. That's it. That's what's like the one. Yeah, want the whole molecule. No, really, I just made it up. Oh, that'd be no, it's soft. Well. It would turn into a chance. Yeah. But it does just take it solid.
Oh, I'm sure.
Probably, it looks like a directing. Directing group molecule. Where's the thingy? What is the thing? Come on. Eh.
Would be good.
All right. Oh. Oh, that's okay. Okay, do we have some volunteers to come up and label some groups?
Can I ask you if my thing's right?
So that is a part, it is a part names, but what's the name of that thing? And then for I still think
Like what?
it's also group names, so they have like fire.
Another one, right? I still don't know if this is right though. No. Yeah. Just be careful. Yes. Think of it. I mean, we're still trying and it's courage. Do you get creative on courage?
Now we're on the exam.
The credit, like.
Oh.
Right. But. Looks like it on the paper, or like, looks like it was right. Yeah. Like, I think they missed it. Yeah, we did do all. I'm not, I didn't be. I looked up, that's one of the. I know, so. Yeah, I'm so somebody else can. We're being humble, we're being.
Sorry, somebody else.
Ray, you got it, that's it.
Yeah, that's when when I was here. How do you spell last name?
Tertiary?
Yep.
Yeah, it's tertiary.
Amy. But, was, I was thinking of the sex of it.
Erase the question marks. All right, so we got D is lovely over there.
We got it. No, we're doing. So this side. So I'm not sense. This is. Yeah.
Okay, I'll add in some more as we go. All right. So let's do A first. So we have a carboxylic acid here, carbon double bond to oxygen with an OH group next to it. This group over here actually isn't exactly an isobutyl group, and here's why. So I think what I saw a lot of people said this. I think what people are seeing is this shape there. And that would be correct if two things were the case. One, we didn't have the chlorine, or we didn't have the other side of the molecule. But in this particular case, there's essentially an R group on both sides of this area of carbons. And so really the only functional groups we can label here are go put my A. So this is an alkyl halide. And then if you really want, that's a methyl group. But methyl groups are so common that it's almost, as long as you can see where they are, you don't really need to label them. All right, B, we've got an alcohol or a hydroxyl group, although I would memorize, if you're going to memorize something, memorize alcohol with an OH. Acid anhydride with an E on the end. That's an oxygen with 2 carbonyls on either side. And then we have an amine here, a nitrogen atom, and it's tertiary because we've got 1, 2, 3 carbon-based groups.
Wait,
attached.
the OH?
This one?
Yeah.
Acid anhydride. It was correct. I just wrote it bigger.
How did my nose?
All right, and then we've got alkyl halide there as well. So if you like, you can label the methyl group, but whatever. Cool. Okay, C, we have a phenyl group or an arene or a benzene ring. Any of those work for that one. In the middle here, we've got a nitrogen atom directly next to a carbonyl, CO double bond. That's an amide, not an amine, but an amide with a D. And this is secondary because the nitrogen is attached to 2 different things. And then we have another nitrogen down here that's only attached to 1 thing. So that's a primary amine.
Yeah, I thought oh wait, the nitrogen is attached to 2 things. Or no, is that one thing part of?
Well, it's attached to it's got 3 bonds. 1 bond to a carbon and 2 bonds to 2 different hydrogens. But for the primary, secondary, tertiary business, we're only concerned with how many carbon-based things it's attached to.
Let's see.
Okay. Yeah.
Oh.
Okay, for G, we've got a tertiary group. At the bottom. And then we have 2 carbonyls here. One of them has carbons on both sides. So what is that? Yeah, it's a ketone. And then this one has a carbon on one side and it's got a chlorine, a halogen on the other side. So that makes it what? Yeah. Acid halide, acyl halide, or if you really want, you can be specific and say it's an acid chloride, or if it was something else, that particular halogen. Okay, everybody got this or got a picture or something? Because I got to erase. 5, 4, 3. All right.
All right, we have some fun ones at the bottom here. This. That for about color H stage. Yeah.
Yeah. So it's, yeah. So I think it's. Well, responsible. I'm 100% with that. If I'm not sick, you should go off. Relax. I'm actually around 100% positive about anything. Yeah, I'm feeling the words. It wasn't just. I didn't put the focus. Figures, but this is it's a lot of standards. Here's what's wrong.
That's cool.
Okay, what about this weird thing down here?
Let's say one of those, let's say one of those things that you hit, then you pull it up and like the thing. I don't know what it's called. Like, the measurement, the little triangle that you like hit, it kind of fills out.
Hmm. Oh, yeah. So it might look something like this sometimes. Come on, it's on the chart. Yeah, it's an epoxide. So often they don't have that many things attached to them. It leaves. Epoxide. Yeah, so a three-membered ring with oxygen. That's an epoxide. We've got two of those, which are what kind of group? Yep, alkenes. These aren't really alkenes. They're sort of a special case because these are aromatic. In these cases, these actually aren't phenyl groups. Phenyl groups can only have one attachment point, but if you said phenyl, that's okay as well. What else? Triple bond is what? Yep, alkyne. Make sure when you see this sort of symbol, this isn't like a weird functional group with all sorts of other atoms on it. This is just an ethyl group, so just two carbons. CH2, CH3. Okay, then we've got these three, which are actually all the same. And these are written differently than what it looks like on your chart. So one way we can make it look more like your chart is to replace, well, first I'm going to replace the Me with H3C. All right, and so over here is the rest of the molecule or something. Each of these is a carbon-based group, right? So we can erase that and just say that that's R. And then in the same way, the CH3, we can also call that an R. So now what do we have? Yeah, these are ethers. What else? Oh, I think there's only one thing forgetting, and that is this alcohol. We've got a quaternary amine here, nitrogen with 4 things attached to it and a positive charge. In this case, the bromine is just the counter ion to balance out the charge.
Wait, it's not alcohol, it's OH, not HO.
Ah, good point. So if the bond is coming in like that, then we write it with the OH, because what we actually have in this case is a bond and then an oxygen and then the hydrogen. But if it's coming off the other side of the molecule,
No, but HO, like, if you put OH, it's like it's binding some hydrogen.
exactly. We want to make sure that we show that the bond is to the oxygen. And so that's why we write it backwards in that case. Okay, quaternary amine. We have a secondary amide. Saw that in the last set. An aldehyde here, a carbonyl group with 1 carbon attached and 1 hydrogen attached. That's the key here for the aldehyde, is the hydrogen. A peroxide is an oxygen-oxygen single bond. Those are pretty unstable, so we won't see them very often. A thioether, I guess I'll be more specific here and say that just the sulfur and the 2 things around it are thioether, but that's fine. It's like an ether, but with sulfur or thio. Okay? And then we have CN, that's a nitrile or a cyano group. Of course, for nitriles, nitriles can look different in a lot of different cases. So CN is common. You might also see C triple bond N. And I think that is also fairly easy to see. What's more difficult is when you have something like this, where the carbon is not explicitly drawn. And some people think that's an amine, but an amine only has single bonds. In this case, those are all nitriles. In organic chemistry, we usually use the word nitriles. Cyano comes from cyanide, right? CN minus is the cyanide ion, and so that's sort of an inorganic name for it, but same thing. I also should mention that this up here, sorry, people who have already taken pictures, isopropyl group. I don't think I'm missing any other.
I just spelled the 2 ones at the bottom, V was P and one's A. Is that outside?
Peroxide,
Oh, peroxide.
oxide, and aldehyde.
In week long lists, we're always supposed to keep everything as full and make sure they're responsible. Makes it oxide look really weird. Like,
Yes. So the reason that I did that is because often the hydrogens are drawn in, and yeah, I don't know. It's okay to break the rules in that case. But yeah, I suppose really you should kind of try and do. Nope. Maybe, I don't know. Yeah, it's hard to make them, they never look very pretty. All right. All right, see if you can come up with some IUPAC names for these.
Both of those. I got the last one that was not. I have a question, how is it 236? Are you just going from the bottom up?
So I started here. 1, 2,
Up.
3, 4, 5, 6.
Okay, so you want to start with the one that will be the SO group's earliest, right?
Correct. So in this case, regardless of whether you start on the left or the right, you're going to have a methyl group on carbon 2. The question is, there's this methyl group. You want that one to be as low as possible then. And so that would put it on carbon 3. Okay, F and H both have 2 answers that are, for our purposes, equally correct. The differences in the answers only have to do with the numbering. All right. Because both of the names have substituents on the same numbers, just different substituents on those numbers. So for F, we can have So for this one, it's either 3-bromo 2 isopropyl 1,4-dimethylcyclopentane or 2-bromo 3 isopropyl.
Do you know what nickname for this? You just say it.
Yeah, so I don't know if this particular compound has a common name. Generally, in what happens in the chemical literature is you have, a bunch of compounds in your paper, and at some point you refer to this as, oh, we're going to call this number 34, or, if it's the 34th molecule in the paper, and then you just refer to it as 34 or whatever for the rest of the paper. But yes, they do get heinously complex very quickly. And then for H, four chloro 5 ethyl or 5 chloro 4 ethyl. Okay, what questions do we have on these? Are we happy with A?
So if you already found A, does it start from the left to the right, right?
Yes.
Can you go for B?
D, yes. Okay. So, yeah, well, let's go through all of them in order. Okay, B, make sure you count your carbons. You should get 7 carbons in the ring. So that's our heptane.
So where would we start? Would we not start with B, or would we start somewhere else?
So we're going to start inside the ring. And well, there's really 2 places that we could start. We could start here or there. If we start at the first option, that's going to put 2 of our substituents on carbon number 1. And then if we go counterclockwise like this, 2, 3, 4, 5, 6, 7, that puts our only other substituent on 3. So that gives us a 1, and a 3. If we did it the other way, started at the top and went clockwise, that would give us 1 substituent on carbon 1 and 2 substituents on carbon 3. And so we want more substituents on lower numbers. So that's the numbering scheme that we're going to follow. Okay, then identifying the functional groups. So CH3, I think we know that's methyl. CH2CH3 is ethyl. And so another way we could have written this is just 2 carbons like that. Or like I did in the functional group example, ET for ethyl.
So you're only counting the carbons, right? That's why the 2 on the top are methyl groups.
Correct. Yep. So 1 carbon for each of the methyl groups, and then 2 carbons, CH2, CH3 for the ethyl group. And of course, remember when you've got a bond drawn between a carbon that's not shown and a carbon that is shown, the end point of that line, so the southeastern point of this line, doesn't add an extra carbon into the mix. So there's a carbon right there, and then the next carbon that's attached to is the one that's explicitly drawn out.
I don't see that. What about D?
Oh, so let's we kind of already did C a little bit. Yeah, so we'll start going from left to right in order to keep this methyl group on carbon 3 rather than having it end up on 1, 2, 3, 4, carbon 5. Okay, so for D, again, we've got a ring here. It's a 6-membered ring. And we want to start on like we did in the above example, we want to start on the carbon with the most substituents. If we got a ring. And so that's going to be there. Now, do we want to go clockwise or counterclockwise?
Counterclockwise?
Well, if we go counterclockwise, 1, 2, 3, 4, 5. So that's going to put our substituents on 4 and 5.
So are we going around the ring or can we not, or do we have to go around?
Yep, you have to go around the ring. Yeah. So we go clockwise, and now we have our other substituents on 3 and 4. Other potentially not tricky, but a spot where you got to be careful is counting the number of carbons in these longer chains. Three in the top one, so that's propyl. 4 is butyl. And the fact that the propyl chain is on carbon 3 and the butyl chain is on carbon 4 was an accident on my part. A coinky-dink. Okay. Okay, E should be the most straightforward. Are we happy with E? Cool. F. Well, we've got our 5-membered ring, cyclopentane, and we can do two. I'm going to zoom super in here. Hang on. We can go this way, 1, 2, 3, 4, or 1, 2, 3, 4. In either case, we have a substituent on all of the carbons from what? Oh, sorry, I should do. Well, this is 5 either way, huh? Yes. Sorry. Regardless of which direction we go, we have one substituent on 1, 1 on 2, 1 on 3, and 1 on 4. There is a rule as to which you should pick, but we're not gonna bother with that in this course. And so then it's just a matter of picking if you want to do the blue or the red. And sorry, if you do blue, it's sorry. Blue has bromo on 2 and red has bromo on 3. We don't start the numbering on the bromine because that would not minimize the substituent numbers. Additionally, the fluorine example that I did right at the beginning of class, where we had the fluorine on a carbon dangling down off of what looked like the parent chain, that's not an issue here because the parent chain in this case is always going to be that ring. Okay, G. We have a cyclobutane, a square. And again, we want the number 1 carbon to be the one with the most substituents. That one. And we can say, all right, we'll go counterclockwise. That puts the butyl group on 3. 1, 2, 3, 4 carbons, butyl. Or we can go clockwise. 1, 2, 3, 4. And same thing. Yep, it's always gonna be on 3. All right, finally for H. We can start over here on 1, 1, 2, 3, 4, 5, and 6, 7, 8. Or go like that. And let's see, chloro on 5 is red. Chloro on 4 is blue. And again, so this is like the case just above where we can go either direction and it still minimizes the substituent numbers. Also, one thing to watch out for here is this looks like 4 different types of functional groups. We have the end of a line, we have an ethyl group, we have a chloride, and we have a CH3. But remember that this here is also a CH3. It's just written in a slightly different way. Questions on those? All right. Next time, make sure you bring your homework and we'll start talking about IR spectroscopy. All right.